Coming up next, we have a new. I really apologize for if I'm mispronouncing your last name. Niru Maheswaranathan. I apologize for that. Niru received his PhD in neuroscience, working with Surya Ganguly and Steve Backus at Stanford in neuroscience. He is now a Google brain, and he works very much at the intersection of machine learning and neuroscience. And he will present his work on understanding the dynamics of learned optimizers.
Yeah, thanks very much for all of you for attending, and thanks to the organizers for putting together such a great conference so far. My name is Niru Maheswaranathan, and I'm excited to talk to you today about our work on understanding the dynamics of learned optimizers. This is joint work with David Cicillo, Luke Metz, Roxy Sun, and Joshua Soldigstein. So the general category under which this work falls is what I like to think of as reverse engineering learned algorithms. And let me explain what I mean by that. The way I like to think about it is deep learning really gives us a new kind of superpower, and that's the ability to learn algorithms as opposed to having to have humans design them. So for example, we can specify some objective that we'd like our algorithms to accomplish, and then use deep learning to discover or train algorithms for that purpose. Now, there's a drawback to these learned algorithms, which is that they're very hard to interpret. So for example, these are like black box learned algorithms, and they're hard to understand. And this makes it difficult to, say, diagnose failure modes of these algorithms or propose improvements, or even to see connections between these learned algorithms and existing or known methods. So this is kind of the general space I'd like to think about. And in particular, I'm interested in taking learned algorithms, reverse engineering them to understand or discover what exactly they're trying to do. So today we're going to be talking about that for a specific type of learned algorithm, which are learned optimization algorithms, or learned optimizers for short. So first, we'll go over some background. I'll explain exactly what I mean when I talk about learned optimizers and why they're so interesting. And then second, we'll go through some methods we've developed for understanding and analyzing optimizer behavior. And then finally, we'll use those methods to try and dissect learned optimizers and show that they've learned both known and novel mechanisms when trained on different kinds of tasks. Okay, so first, background, what exactly are learned optimizers? So again, we're thinking about optimization algorithms. Optimization is a core component of machine learning and deep learning generally. And the goal in optimization is to minimize some loss or cost function f over some parameter space x. So I'm going to refer to this as the target optimization problem that we'd like to solve. And today's work, we're going to be thinking about first order optimization algorithms. So these are algorithms which have access to the gradient of the loss with respect to the parameters. And I'm going to use G as a shorthand for referring to this gradient. Now, there's kind of a rich, diverse history of different kinds of optimization algorithms which have been developed for running first order optimization. So here's just a sampling of some of these different techniques: momentum, AdaGrad, Adam, and even other kinds of innovations like gradient clipping or things like learning rate schedules. And what unifies all of this work is that they're really, the provenance of these algorithms or ideas are really designed by humans. And they're based on theoretical principles or intuitive mechanisms. And this intuition is really useful. For example, it allows us to, combine different ideas from different optimizers, identify particular problems that certain optimizers are really well suited for, or even like identifying flaws in a particular optimizer. And the reason I'm bringing it up this way in terms of like these are designed by humans is to contrast this like rich history of optimization with newer work, which is trying to learn optimization algorithms or discover optimization algorithms. So in this thread of work, what we're trying to do is automatically discover optimization algorithms through some kind of meta learning procedure. So I'll explain how that works in a second. So the idea here is, we have some problem that we'd like to optimize. So these are the parameters we'd like to optimize at, say, iteration or step k. So that's the parameters xk. We query the function that we're trying to optimize. So we compute the gradient with respect to those parameters. And now we feed that gradient in to this learned optimizer, which you can think about as just some function capital F here. And that learned optimizer is parameterized by some meta parameters theta. And so theta kind of controls or governs exactly what this function is doing. And the job of this function is now to spit out updates to these parameters. So it returns, the parameters at the next iteration. And so then we can iteratively apply these computations and this carries out effectively an optimization algorithm. And then there's one other thing I should mention, which is that, you know, in the way I'm currently showing this optimizer only gets the gradient as input and only returns the parameters. So there's no state or memory to this optimizer, but oftentimes we want optimizers to have some state or retain some memory about the particular optimization problem being solved. And so we can add that into these learned optimizers. So I'm going to use H to represent some optimizer state. And so now this learned optimizer takes in two inputs, the current gradient and the current optimizer state, and outputs both a new optimizer state and as well as the updated parameters. And so I haven't really gone into exactly how we parameterize this function f. So what's the shape of f and how do the metaparameters theta look? And I'm not going to get into those details. In this work, we're using recurrent neural networks to parameterize this function f. But for everything I'm going to be talking about, you can just think about it as some function which has metaparameters theta. And so now in order to actually train this thing to do optimization, we need some way of learning these metaparameters or training the metaparameters. And so we do that through a gradient descent process. What we do is we unroll a big computational graph where we iteratively apply this optimizer and then backpropagate through that graph in order to compute derivatives with respect to the metaparameters theta. And we can use those derivatives to then train the optimizer. And again, I'm not really going to go into the details of this training procedure. Suffice it to say, we can do this, it works well, and we can train optimizers that work well on problems of interest. So just to give you an example of that, so I mean, these learned optimizers really can outperform existing well-tuned baseline methods on problems we care about. So in this work, what we did was we trained learned optimizers on 3 different types of optimization problems. I'm again not going to go into the details of what those are, but they cover kind of a large range of different kinds of loss surfaces, from convex to non-convex, low to high dimensional, things with saddle points and so on. And so what I'm showing here, I'm going to show the performance as a training curve. So here I'm showing the loss on the y-axis, and I'm going to plot that against the iteration or step. And I'm going to do that for 3 different baseline optimizers, RMS, prop, momentum, and atom, as well as a learned optimizer. And so for this task, you can see the performance here. This is showing the mean plus standard error over some number of random seeds for initializing the optimization problem. And you can see the learned optimizer performs very well. Even though you might notice that it looks like it's starting to underperform momentum here at the tail, on the actual objective that this learned optimizer was trained to minimize, which is the sum or average objective over these 200 steps, it's actually outperforming momentum because it gets lower loss values early in training when the loss is quite large. And this is for one task. We can change this, change the optimization problem that we train it on. And again, you see very good performance where learned optimizers consistently outperform or beat these baseline methods. And each of these baseline methods are tuned for these specific problems as well. So they're well tuned. We're tuning all of the hyperparameters for these baseline methods as well. So whenever I see performance plots like this, it's great that we get good performance out of these learned optimizers, but I'm always left with trying to understand, well, why or what exactly are these learned optimizers learning, right? Like, why are they able to outperform these careful hand-designed optimization algorithms? And so that's kind of the central questions of today. First, what algorithm are these learned optimizers learning? And second, how is that algorithm implemented in the learned optimizer? Okay, so to answer those questions, first we're going to have to cover some methods for understanding and analyzing optimizer behavior. So there's going to be 2 methods I'm going to talk about. The first is what I call update function visualizations, which sounds like a lot of jargon, but it's actually a very simple idea. So the idea here is, you can think about an optimizer as just some mapping from a gradient to a parameter update. So here, for example, in gradient descent, the parameter update, or how we change the parameters, it's just proportional to the negative gradient. And the slope here, the proportion, is given by the learning rate alpha. And so, for example, we can just plot this. It's just a one-to-one function. We can just look at it. And so for gradient descent, again, it's very simple. It's just a function with a negative slope, a linear function with negative slope. But gradient descent is simple in particular because it's a stateless optimizer. There's no additional state in gradient descent. Things get a little more complicated when we start to think about stateful optimizers. So the simplest one to think about is, say, something like the momentum algorithm. And in momentum, which I'm showing here, the change in parameters depends. So there's a term which also looks like it's proportional to the gradient, but there's this additional term which depends on the momentum state. So here, beta is like a momentum timescale or the momentum hyperparameter, And V is like an optimizer state variable. It's like a momentum velocity, as it's called. And so what I'm plotting in these different colored lines is exactly this input-output function. So the parameter update as a function of the gradient, but I'm plotting it for different values of this velocity variable V. And as you can see, what the effect of the momentum state is to induce like a vertical shift in this update function. So it's momentum is still a linear function, but now it has this vertical offset. And so you can kind of do this procedure for all kinds of optimization algorithms, right? So for example, we've seen this for gradient descent and momentum. For things like gradient clipping, where you often clip the gradients beyond a certain threshold, that looks like a saturating update function. And then there's other optimizers. For example, here I'm showing RMS prop. If you're familiar with that, it's like Adigrad. It's one of these optimizers which has adaptive learning rates. And the way those learning rates adapt is they are adapt to some estimate of the gradient magnitude. And so the state variable keeps like a running average of that gradient magnitude. And as you can see, as I sweep that state variable, just as I did in momentum, you get a different effect in this update function, namely the slope changes for the update function. You can think of the slope as like a measure of the instantaneous learning rate. So, you can have steeper learning rates or shallower or smaller learning rates. So again, I'm showing these for all of these optimizers where you might be familiar with these already or have some experience with them, because to kind of get you familiar with these functions. But this visualization works for any kind of optimizer. So, you condition on a hidden state, you just plot this one-to-one function. And so in our optimizers, things get a little trickier because we don't have these low dimensional state variables. For example, in momentum and RMS prop, there's only a single state variable. In our optimizers, they're parameterized by neural networks, and they're going to have very high dimensional hidden states. But actually what we're going to see when we get to the results is that there's low dimensional subspaces within these high dimensional hidden states where you actually see very structured or understandable changes. And the way we're going to see that is by visualizing these update functions along those subspaces. Okay, so that's the first tool. The second tool is understanding the evolution of the state dynamics. And to do that, we're going to use tools from linearization. So we're going to linearize the optimizer dynamics around approximate fixed points. So let me break that down. So this again is just an optimizer state update equation. So here, if you remember, H is what I was using to call the optimizer state. And G is just the input to the optimizer, it's just the gradient. So you can think about this as just like a discrete time dynamical system, which is governing the evolution of the state variable H. And the gradients are actually just inputs to that dynamical system. Now, from this perspective, what we can do, okay, so again, this is the full nonlinear update. But what we're going to do is instead of, this is in general a nonlinear dynamical system, what we're going to do is replace this with a linearized approximation. So we can do a first order Taylor expansion of this function around a particular linearization point H star. And that lets us now write down a linear dynamical system which governs the evolution of the hidden state near the fixed point H star. And that's useful for a couple of reasons. Namely, one, it's very easy. We can understand and intuit linear dynamical systems much better than nonlinear dynamical systems. We can even go a step further. So in particular, if we focus in on this matrix here, JH, that's what we call the recurrent Jacobian. It's a Jacobian matrix that governs the dynamics here. And in particular, what I can do is rewrite this linearized equation in terms of the eigenvector basis of the recurrent Jacobian, right? So if you recall from linear dynamical systems, if you rewrite things in terms of the eigenvector basis of the dynamics matrix, everything decouples. And so then we actually get a much simpler, optimizer out when we do that. So for example, here what I've done is I've just rewritten this equation, but now in terms of the eigenvector basis of JH. So just to walk you through the variables, VI here is the projection of the state onto eigenvector I, eigenvector of JH. And in particular, beta here is the ith eigenvalue of JH. And I'm choosing these variables carefully, V and B, to draw the comparison to momentum variables, namely velocity and the momentum hyperparameter. So just for a comparison, you can see the classical momentum state update equation looks exactly like what we're getting when we do this, rewrite this thing in terms of the eigenvector basis. So again, this is the classical momentum algorithm. You take the gradients, multiply by a learning rate, and you maintain this velocity state V. So okay, so just stepping back out for a second. So the idea here is that near approximate fixed points, optimizers implement momentum. And so you might wonder, well, if they're just implementing momentum, what else can they do? And it turns out that the way they implement more sophisticated behavior is by inducing dynamics that take you away from approximate fixed points. And so basically what we're going to do, we can stitch together these different local pictures. We have local pictures around approximate fixed points, and we can stitch those together to get a global picture of what an optimizer is doing. Okay. So now to touch on the results. So what we're going to do is use these methods to dissect exactly what learned optimizers are doing. So the first, I'm going to kind of do a deep dive on a particular mechanism, which is momentum. And as I've alluded to, we think that's implemented through linear dynamics. So what I'm going to show first is a low dimensional projection of the high dimensional hidden state dynamics. In particular, I'm using PCA to make this projection. You can see I'm using PCs 2 and 4. The reason it's not, say, 1 and 2, for example, is that different mechanisms are actually implemented in different PC subspaces. So I'm only showing the projection that highlights the momentum mechanism here. But what you see in this subspace is basically there's a single fixed point which is governing the dynamics. And all these gray circles are different hidden states along the trajectory when I apply an optimizer on a particular problem. And you can see the dynamics are really organized along this like one-dimensional line in this state space. And we can understand exactly what's happening along this line by using these update function visualizations. So that's what I'm showing here. Each arrow corresponds to a different point translated along this one-dimensional line. And now I'm plotting on the right the corresponding update functions as I move along that one direction in this high-dimensional state space. And what's remarkable is along that single direction, you see exactly this vertical shift that you would expect that we see if you're doing something like classical momentum. You can even go a step further, and then, so this is kind of like a qualitative picture. You can like ask quantitative questions like what's the exact momentum timescale being used here. You can do that by computing the Jacobian matrix around these fixed points and looking at the corresponding eigenvalues of that Jacobian. So on the right, I'm showing these eigenvalues in the complex plane. They're colored by the effective learning rate for each of these modes. And in particular, there's one point, this purple point, which I can write down the effective learning rate and momentum value for that mode. And that exactly corresponds to the dynamics along this one dimension. And so this is all for a particular optimizer trained on a particular task, but actually we see this exact same kind of behavior across optimizers trained on very different kinds of tasks. So here you can see, each column is a different task, but in each column you see the same picture. Basically, there's a global fixed point, dynamics are organized along one direction, and as you move along that one direction, you see this vertical shift. So that's for one particular mechanism, which is kind of like what's occurring when I zoom in around this fixed point. But there's also other interesting mechanisms going on. And unfortunately, I'm only going to be able to really just briefly touch on what these are. So for example, we see evidence of gradient clipping. That's exactly like this saturating of these update functions, which I showed before. So we see that for certain tasks. And depending on the task, the optimizer might operate more in the linear portion or more in the saturating portion. We also see evidence of learning rate schedules. These are implemented in a really interesting way through autonomous dynamics of the hidden state. So for example, this trajectory here indicated in blue is an autonomous trajectory. So I'm not feeding in any gradient, but there's autonomous dynamics that take the state from the initial condition to this final fixed point. And as you move along this state, if you look at the update function, the slope of the update function, it actually changes in a way that kind of implements an effective learning rate schedule. And then finally, we also see evidence for kind of new way of implementing a learning rate, a way of doing learning rate adaptation. So again, learning rate adaptation is where you want to change the learning rate depending on gradient magnitudes. And we see that through, implemented through input dependent fixed points. But the thing to take away here is these different arrows are pointing to different points in the state space. And if you look at the update function associated with those points, you exactly see this slope change that you expect from something that's adapting the learning rate. I think I'm just going to summarize now. So the general goal of what I'm trying to do here is understand exactly what learned optimization algorithms are doing and how they're doing it. And what we see in this case is that analyzing these learned optimizers reveals interesting canonical behaviors, things like momentum, a new kind of learning rate adaptation, gradient clipping, and learning rate schedules. And if you're curious about exactly how these are implemented for different tasks and how they vary across tasks, I'd encourage you to check out the paper. And thank you all for your attention.
Thank you so much, Niru, for the thought-provoking talk. This was really interesting. Again, because of time and because we want to be respectful for people who are joining in different and complicated time zones, We will have to postpone the questions for later, but let me remind everybody that we do have a happy hour and a socializing virtually hour at the end of this session. So I encourage everybody to attend and to keep the discussion live there. So thank you again, Niru.